Good evening. I'm audible. I'm audible. Anyone? Okay, fine. So we welcome you all on the day 4 of our FDP on fundamentals of smart grids. So sir is with us. So we welcome sir once again for giving his valuable time to deliver the talk. So without any delay, we start and sir, over to you.
On to the course on fundamentals of smart grid, and today we'll be talking about yes. In the past, such as the previous lecture, we talked about battery at large, and today we'll be focusing on battery management system. Now, one important question that comes to my mind that why do we go for BMS? I do not know how many of you have really opened a battery. You will find actually many cells connected in parallel. And these cells slowly discharge. Over a period of time, the capacity to charge and discharge get reduces. And we finally it is the time to replace the battery. Finally, it is the time for the replacement of the battery. So, just an example, if you have two batteries, the completely discharged, has no strength, and other has full strength. Now, can we carry out charging and discharging of the battery, which has two cells connected in parallel, and one cell which is completely discharged, and the other is actually fully charged? I think the answer is no, because when you connect two cells in parallel, it to be of equal capacity, then only you can carry out charging and discharging of batteries. So battery management system is responsible to make sure that all the capsules connected in parallel, which are hundreds in number, being packed in a box. So when you see, we say it is a lithium. Normal pencil batteries that we use at home, each and every lithium cell will be like that, and you find hundred of cells got packed inside it. So it is very important to make sure that all the batteries, life or the capacity or the strength or the density should not deteriorate drastically compared to other cells. So that is the main focus. So to avoid that, actually, we are trying hard to make sure that, unbalance is quite common, but those unbalance need to be rectified very. When we talk about the philosophy, we'll also touch upon a bit of energy storage technologies, battery management system, monitor. Today, the biggest challenge what we see in this country that we have enough batteries, but unfortunately we do not know how to repair. We do, we simply throw it up, okay. So there was a time we talk about cartridges in printing machines. In the past, we started throwing it. Over a period of time, actually, we started refilling it, okay. So similarly, it is important for us to know the technique of BMS, which is very, very important. And when you see a battery pack in the front or in the back, you'll find a complete digital circuit, which is nothing but truly a BMS. Takes care of the complete charging of a chargeable, rechargeable battery or cell. Now, over a period of time, actually, we got many techniques, but one thing you can very clearly see, the, energy density, if you see Y-axis versus the volumetric energy density, isn't it? So, the lithium ion, the middle elliptical circle, the maximum energy density that you can experience in the Y-axis, okay? And that's why today people say lithium ion is quite popular. And there are two types of lithium ions. One is lithium ion C type, the other is lithium ion P type. And C type is mostly cylindrical type, and P type is known as actually prismatic type actually. So there are two varieties of the characteristic of different chemistry, and it has been found more or less the lithium ion is really a good one for any rechargeable application. Batteries, they are lithium ion. For an example, your mobile phone is the best example. All right. So they can be charged and recharged, and even perhaps for some extent they are working till unlimited. Your mobile gets spoiled, but the battery is still working, which is quite interesting. In early days, actually, the battery we need to replace. We buy a new battery, and Apple changed the history recent advancements in lithium batteries, solid state electrotype, silicon based anode unwraps the opportunity to use any rechargeable application. Lithium ion happen to be the best combination. Now, if you see a bit of application of lithium ion, your smartphone, but let us closely, if you talk about the gradually saturated market, let us focus on that. Smartphones, laptops, tablets, power tools, and personal care like saving kits and other devices in which we use lithium ion, which is almost a saturated market. However, there are a couple of actually growing markets, one in the field of actually electricity grid, the other in the field of actually transportation. So transportation market, we use it for actually, scooters, buses, and perhaps the very common popularized. And now slowly we are trying to move towards trucks, heavy vehicles, and almost why not even up to aeroplanes. Today we are talking about batteries for aircrafts, isn't it? Already the first model is tested, and very soon we will fly an electric vehicle based aircraft. Okay, or I can say electric battery operated aeroplanes, right? It's like sitting on a bomb and driving, isn't it? Quite exciting. Now, moving to another growing market is about electric grid, where we talk about energy storage systems. Their main job is to, supply electricity to the distribution systems, number one. And then renewable energy storage technology applications, grid energy applications, and also it's like a suitcase size, we can pull it and plug it and use certain applications and then bring it back. So if you see the application of lithium ion battery today is huge, very, very huge. Now, there are a couple of merits and demerits, you know. It is not that lithium-ion battery advantages that need to be highlighted. So it is, first of all, very, very lightest metal with high potential difference and up to 4-volt nominal. So that is, it's good to carry. It's not as heavy as for the similar kind of energy density. It is almost very, very light. And it is commercially available with gradual reduction of the cost day by day. The cost of lithium ion is keep on reducing. That is one more advantage. Provides high energy density and power density both. As I told you, both energy density point of option. And one interesting part, many times you might flying or keep your mobile in aeroplane mode, and when you get down, if you again come to a normal position, you see your battery percentage. If it is 23%, it will remain 23. So that means it has no self-discharge mechanism. All right, lithium ion has no self-discharge mechanism. So that means even if you keep it off for some time, it is not going to discharge completely. Now, flexibility in cell types, that is right technology used for specific applications. But the limitations are quite challenging. It requires a constant monitoring and protection. Perhaps it is there everywhere. It's expected to reduce, but it's still not reduced as expected. It's still expensive device. And every now and then, a derivative of lithium ion is combination. So we are not completely free from lithium. That is because it just comes commercial item. It took still another couple of days. The longest solution mankind has experienced a good technology happened to be lithium. Okay. So what is the need of actually a BMS? So it reduces the risk of prematurity of the battery and optimal usage of energy inside the battery become an issue. Part of all types of energy storage, especially for sensitive batteries like lithium ion. It enhances system runtime reliability. Probably the life, which is very importantly, the reliability and efficiency of the battery can certainly management system, its operation, how does it work? So first of all, you have a battery, which can be connected to different devices to measure its current, voltages, and also its temperature, which is very, very important. Many of you may be aware that the life of the battery, you see, when you touch your mobile, the moment it get heated up, okay, so the mobile is actually heated up, that means you can conclude that your mobile is very soon to be replaced. Okay, so to die. So that is one, current voltage and temperature need to be monitored. And then you have to monitor the SOCs, you have to estimate the SOCs. And then state of charge, then state of heat, and then you have two batteries or two cells. They are not equal. All of you can see the diagram, the basement diagram. One capacity at a given point of time. And this is not a good thing for any battery's life. So we need to balance it out. and hence we connect for charging and discharging. So as and when you connect it for charging and discharging, we expect all the battery to be of equal capacity. All right? And that is nothing but your battery management system is all about. And as I told you from the beginning of my lecture today, if you have two batteries, one is completely discharged, one is fully charged, it's not a balancing mechanism. But if you do not have a proper BMS to balance all the cells, finally, because of one, then all the 99% cells also will stop charging and discharging. So just due to one cell, stop charging and discharging. So we should not allow at any given point of time, even a single cell dried out first compared to other cells. So we are trying our level best to make sure that they all die at the same time. Okay. So because the interesting part actually when it has been manufactured, you cannot identify one pack and replace it. That is very, very difficult task because it has digital connections, it has power devices connected. Mechanism. So BMS is a complete digital circuit. So perhaps repair is no more possible. So to make sure that the BMS device actually takes care of the rest of the things. Now, so first of all, we need to monitor the health of each and every cell, and then you manage. Okay, so you need to understand which one is really not doing well. Sensing IC for monitoring. So SOC of each and every battery, okay, need to be monitored. And once they're monitored, then only you can take action that how to balance them. All right. So the parameters that can be sensed directly from a battery cell are current through the circuit, terminal voltage, and ambient temperature. So you could see schematic diagram for 680, and you could see on the first monitors with these cell connected. The pink one is your basic cells. The balancer company, cell manufacturing company, basically. So there I could see how BMS is working. It's very nice. And they have actually thousands and thousands of cells are being actually balanced before packing. Okay, though they are not manufacturing their own, they're getting from somewhere they're importing. But what they do, they import and they don't know what is the battery's state at this point of time. So they use BMS and then they pack it. And then that is ready for cells. Am I right? And once they or cycles or small two-wheelers, so there they don't have actually a serious BMS technology because that will be very, very expensive. So they simply, once they balance it and dump it, and slowly it dies out. Okay, it depends on actually how to use it. But if it is a costly device like electric, BMS also intact with your battery packs. So first of all, we need to understand very important. There are many methods. There are few, but today there are almost 30 to 40 odd methods available. SOC estimation is a very, very important concept because what they say. Let's say I told you once, I guess, I'm repeating it. You have a laptop, you look at the battery, which is going to be X percentage, let's say 20% battery. You shut down. After 2 days, you switch it on, you see it is 7%. Okay. So what does it mean? That means somewhere your SOC actually, that capsule that you see. And that SOC measurement, what we do, more or less a heuristic way of doing it. Actually, it's not a very expensive mechanism we put it in any devices because it's not going to impact me. But for electric vehicle, battery, it is showing 20% instead of 5%, and suddenly it goes down. Many times you realize it was there 20%. Let's say SOC is not the right one. So for a linear phase, it will show a wonderful range. We'll answer all your questions. Any challenges? I could see some messages. What do you say? Is it okay?
It's okay.
I think probably please disconnect and join again. Probably some issue with your end. Please try to correct it. Am I audible, loud and clear? Couple of you?
Creating some time.
Is it okay now? Am I audible now? Okay, great. So that is how the, yes, thank you, Sanjeev. So we have probably like conventional methods, and in which we have a couple of actually sub methods. They are open circuit voltage method, electrochemical impedance method, model-based SOC estimation. We have adaptive filter methods, Kalman filter, sigma point Kalman filter, learning algorithm, neural network, fuzzy logic, observers, advanced algorithms like deep learning and hybrid algorithms. So there are many algorithms. Conventional, adaptive filter, learning algorithm, nonlinear observer, and hybrid methods do have certain merits and demerits. So I strongly recommend all of you to have a look into this, probably just to understand which method you like to opt for. But I have certain experiences because we spend almost more than 5 years on a BMS, and till today we were not successful. All right. So it gave us actually many challenges, many challenges. So we understood all the so it is slightly riskier field because not fully matured or shared technology on book. Okay, even in publications, people do not disclose the altogether right method. So I could see some suspense is still lying in BMS technology. So we will get into a bit of equivalent circuit model of a battery. The left-hand side diagram we all have seen in the past, okay? So, which is having a battery equivalent voltage source, okay? UOC, popularly known as, then you have a resistance, and then in series with shunt RC circuits till infinity level. That is what the representation. And at the end, you have a terminal voltage, which is V is UT. The voltage UT and UOC, there is a strong relationship. So for this transient circuit, you can calculate, for example, for R1, C1, if the voltage is going to be U1, and similarly U2, E3, UN, the last terminal voltage across RC shunt circuit, you can easily calculate. And the equation 4, which clearly tells you how equal to your RC, right? So if you calculate which will be almost non-linearly increasing. Now, this is one of the standard diagram which helps you to just imagine how the BMS look like. All of you, please have a look. Could you see a battery pack Okay, so you could see the battery module on the, the cell on the top. They are like, pencil batteries sort of thing. And then you have a battery module where 100 of batteries are actually packed together after balancing them. And then you have a battery pack controller, okay, along with the battery module. So the front side is basically your controller that will actually, will take care of your battery management system. So that controller will see to that all the battery modules or all the block diagram for each and every structure, battery pack controller, which is a different mechanism, battery makes a battery pack, which is normally used for any, applications, electric applications. I'll try to explain it slowly. Who will force the battery to be now of imbalance in nature or imbalance characteristics? So what happens? There are two different type of and the other one is going to be a permanent SOH. All right. So the state of charge, which is keep on changing, and the SOH, which is going to be a permanent feature. So all of you please have a look to one of the diagram. There is a charger. So we have a battery, which is a red battery. And then we have another battery, which is 20% filled, for an example. Okay. So what I do actually, and you plug it. Okay, so the plug actually basically converts AC to DC, and then the battery gets charged. Or indirectly, I can have one DC source charging another DC. You might have seen that when a vehicle lead acid battery is not functional, we bring another lead acid battery. So, if the balancing is not implemented, if you do not balance it, the left side you could see, they're all of different steps, okay, the capacities, and all of actually either they are at low or they are side, they are at low capacity, but all are balanced. The right hand side, they are heavily full capacity, but they are unbalanced. Am I right? So, so the concept is that actually few batteries actually get charged fast, and few charges actually take little time to charge to that point. So what happens? I put it for 5 minutes, and there are 100 cells, and 50 of them actually charged. And by that time, another 50 will be 60% charged. So that is where actually battery imbalance come to action, and they need. So the balance is not implemented. If the balancing is not implemented, then the weak cells are okay, they will actually discharge quicker. The moment they discharge, premature than others. So this will slowly die off. Imagine a case where a less capacity cell and a fully capacity cell connected to a load, it will neither discharge or not charge. So slowly, due to imbalancing, actually the battery life will completely lost. It's a PhD problem, to be very honest. But one must be, having a lot of patience in chemistry, must be having patience in. It's an interdisciplinary topic, basically. So power electronics, power systems, and chemistry or chemical, these three combination, three persons can together do one PhD. If one has to do, then one has to develop skills in other two topics. So that is very important. So as I told you, for last 5 years, we were not successful in a sense. We are successful, but actually we have very limited knowledge in chemical engineering. Methods, there are two different types. One is passive, the other one is going to be active. So the passive one is overcharge and pack to pack one. Cell to cell, we have adjacent cell to cell, we have any cell to any, and we have direct cell to charging mechanism or cell balancing mechanism. So because this is here, actually, we are not really getting too much of deeper into the circuit analysis, but for the benefit of you all, I'm just slowly making your life little exciting and tougher by sharing some of the complicated circuit for cell balancing. Okay, so because we have spent a reasonably good time in this field, so I thought let me share all our experiences to the students. Okay, so it's the high charge battery cell voltage. Active balancing is the energy capacity without any dissipation. Okay, so that is your active cell balancing mechanism. So you could see there are shunt resistor, switch shunt resistor, single switch capacitor, multiple switch capacitor, switch transformer, shared transformer type balancing circuits. Now I'll show you another level of actually two complicated cell balancing circuits. Each one has a merit and limitation. Adjacent cell to cell, how they are become, because you have n number of cells connected, and one battery can help the second to third, third to fourth, that is adjacent cell to cell. And you can have any cell to any cell. You have X cell can charge Y, Y to Z, anything can happen. All the A, B, C, D, F, different type of single tired switched capacitor mechanism, double tired switched capacitor, forward flyback multi-binding transformer mechanism. So I think a lot of research has been done. First attempt to do it. There is nothing wrong. Those are very cheaper experiments. We can also have a flying capacitor type, and we do have actually bidirectional flyback converter, quasi-resonant LC converter with boost converters, LC resonant circuits, single inductor switching circuits. So with over a period of time, researchers have made the problem too efficient and too complicated parallel to that, okay? Because in Poltronics, the beauty of Poltronics that you can do many things for the same purpose. Am I right? You can do multiple changes and achieve the same goal. And this, because now almost how many? Around 15 topologies I have demonstrated. So these 15 topologies become 15 transactions and 15 theses. Am I right? Without effective and more creative over a period of time. So ideal, cell balancers, a different type. We have a simple circuit, fast equalization, high efficiency, optimal size of passive elements, less voltage stress on batteries, good balancing speed. What is basically ideal cell balancer is all about, very important, less sensory requirements, economical the device, and apply for static and dynamic balancing. So we expect, but practically it is very, very difficult. So a couple of references you can go through, and we will quickly, with this background, actually now today we'll move to the DC smart grid components. Basically, we'll start with the DC smart grid. So I'll teach a very interesting concept on DC smart grid. The smart grid field. Okay, I'm quite fortunate and happy to share that so we are few those who have actually started Those who have started. What we need to do, uh, I was just mentioning that we were at the time when the concept of actually microgrid is just about to evolve, and probably we are very fortunate to work on in a field which is just upcoming. Okay, and whereas the whole country is talking about DC microgrid that time, we were actually a dozen of researchers. We started working at that time with a lot of risk, but somehow actually we got a lot of success also. So importance of, basically what I wanted to highlight is that we have seen how smart grid research has grown actually. Actually, I was working in one of the universities in UK, and where the library was full of actually DC microgrid, and that was the time where we came across. That was the time where we come across actually. Uh, the importance of DC microgrid, which is important, then DC operation on voltage level, DC microgrid topologies, key energy sources, types of load, switch mode converters, DC microgrid communication, DC microgrid protection, devices, applications of DC, and challenges in DC microgrid. So we'll be talking more or less DC is important, importance of DC. First of all, renewable sources are majorly photovoltaic, which produces DC power. And then you can also see that actually most of the present generation loads like LEDs, mobiles, computer, and electronics loads work with DC only. The electric storage units such as batteries work with DC. So there is a question, why DC, 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 why not AC? Because everything is DC in this world, okay? And always there is a question in mind. I will strongly recommend, I have seen an university where actually the library was completely with DC supply. And for the first time in a very almost 20 years back, I have seen DC plugs. All the plugs in a very huge building are purely DC because which operate with DC, like laptops, and the lights are actually LEDs, and they have renewable PV on the top. So they say, why do I give to the grid? I will generate my own and use of my own way by making the distribution system completely DC. So that was the first time where I learned about DC microgrid. So I realized, oh, this building is completely a DC microgrid. So now next question actually, why importance of DC? Because if you generate DC, if you use DC, actually DC microgrid compared to AC. But many researchers will not agree, already have AC grid, then why DC grid? That is the question came to my mind. So then I prepared this diagram and said, let me ask myself and also ask to my dear students. Isn't it at the end of the today's lecture, we'll discuss why DC, why not AC? So already we have AC grid, then why DC? But still, there are n number of opportunities. I will tell you what. Now, various conversions like AC to imagine if I do have only computers as my load, then why do I convert DC to AC and then AC to DC? My question is directly merits I see in my DC microgrid. I mean, I used to advocate DC microgrid very seriously in my young days, and perhaps actually Manmohan witness how bluntly I support DC microgrid, because we were the first group of researchers in this country who started thinking about DC microgrid in early days. So no problems of reactive power, harmonics, frequency control. But I will also tell you that we faced some certain challenges by going for DC grid, and then we changed to DC-AC hybrid microgrid. So no problem of reactive power, harmonics, frequency control, nothing is required. DC is so simple, no synchronization issues, and controlling become easier. And eddy current, hysteresis losses, and skin effects are absent. Reduces stress on conventional grids, congestion of. So then we must go for DC now. Why we are still going for AC? Is it the case, Manmohan, that going for DC you have no research problem? Because nothing, no problem is there. If you go to DC, there is no problem. Everything is perfect. No harmonics, no reactive power, no frequency control, no congestion, nothing. So when there is no problem, then how can you do research? To do research, actually, you need problems. Am I right? DC is really a beautiful one, but it has certain challenges. As I always say, God is not very kind to engineers. It is true, because the protection of DC grid becomes seriously challenging. Okay, because you do not have a zero crossing. So that has not evolved as of now, maturely. So, for example, high voltage DC circuits, I don't have a protection mechanism that I can easily put it. So probably now it might have come. We have developed our own scheme to protect actually DC network. So that was the challenge we faced, number one. Number two, the spark and the risk associated in the laboratory with 600 volt DC switching on, switching off, the transients, they were so severe, it is life-threatening. So probably handling DC is not that easy as like AC. So there are a few merits and there are a few implementation challenges we have faced for both the DC and AC.
Power level also.
Yeah, you cannot grow as you expect to grow actually. Voltage level, if you see, today we are talking about high voltage DC systems in this country. Economical, the sound is breaking. Oh, I have to regular interval. What to do? Probably this is creating obstacle. Can I take this table? इसको पीछे ले लीजिए. आराम से रखिए. Is it okay? Am I now audible loud and clear? Please say yes or no. Oh, now it is clear. I think Manmohan has created a boundary on the speaker. Oh, you have to be careful. Oh, yes. You see, look, everyone is so happy now. Great. So HVDC, which is the operating voltage range 500 kV and above, and economical and efficient over AC at long distance transmission. So the DC line, HVDC, is always better than AC transmission. Distance. For short distance, it is not acceptable. Now, when you go for medium voltage DC networks, can provide controlled power transfer between 211 kV and 33 kV networks for better utilization of existing networks. And finally, known as LVDC,
and that operate mainly on 48 volt, 380 volt, and 600 volts. Okay, now you may ask me why we are going for 48, 380, and 600. Dear friends, I'm sorry, I have no clue, but it is basically the laboratories, those who explored and conceptualized the DC and the voltage at which they tried and become a fundamental rule, similar to your 11 kV, 33 kV fundamental voltage. But if you wish, we can try with 35 volt, you can try with 200 volt, you can try with 400 volts, no issue. But you will get devices, the auxiliary so we also want to have an experimentation which is of 48 volt, reduces dependency on main grid, reliability to the consumer can be improved, and provides supply to remote villages. So as you know that LVDC network is suited for isolated, okay, grids actually. Now there are different DC microgrid topologies. All of you please have a look into data centers, communication towers, heating equipments, and lighting loads. These are actually basically a kind of loading devices. The consumers who can use this, and the same bus, I need to connect some supply systems, supercapacitors, batteries, wind sources, fuel cells, and photovoltaic cells being connected to the DC grid. Sometime it need to be converting DC. So you can create a single bus in the laboratory, then you can create different sources, including all the kind of generators, all the kind of loads, and you can have some converters, DC to DC or AC to DC, and then you can create a DC microgrid topology, which is very easy to develop. And now the DC microgrid topology, which are kind of topology, we can see to that directly the ESS energy storage systems. This kind of applications are good for voltage range which are close to 48. And with converter, if you connect, then more flexible control and also improve reliability of the system. You can also have bipolar single regulated bus structure, which operate with plus or minus 170 volts. You can decide as per your life. Now, one more topology where we have two different DC sources and they're being supplied and connected. So this is known as multi-bus topology, where we have dual bus separately fed DC microgrids. Simultaneous supply from multiple buses is possible, and hence the total efficiency is improved. So you can have multiple DC buses and cater a single load. Okay, so you can DC and cater to a single S. Is equally important. Every microgrid is able to observe or inject power from its neighbor in case of shortage or surplus. Some corrupted buses can be automatically isolated. I will ask you a question how it is possible. Let's say we have a wish town or a colony which has more than 20 towers, and each tower has actually 40 houses. Right? So I can make each tower become a DC microgrid, and then each tower can exchange microgrid cluster configurations, and then we can have solid state transformer SST enabled DC microgrid in the SST domain. Finally, we move to reconfigurable topology. First one is going to very common ring type in any academic campus. Probably if I go to my IIT Roorkee parent campus, which is a ring structure. each and substation and then supply to a hostel or a department. So DC ring bus architecture, probably MNIT Jaipur may not be a ring structure, it is a radial structure. You just wherever there is power required, we pull it and provide to the colony, provide to your house, provide to your hostel. But there is not a single ring in the campus today. So, which is equally important, which is highly without disturbing other zones, and multi-terminal DC system, which is quite interesting because system connection provide multiple paths for power transmission. So moving to the next arrangement, we can see actually a complete ring type structure. Okay, and we have DC-DC different places, and then we create a DC ring actually, all right. So from the utility, we get energy to a DC bus, and we can also have a diesel generator, which can give me from AC-DC convert to a DC bus supply. I can feed batteries, I can feed through fuel cells, I can feed through PV arrays. Sources, I can just club it together, okay, and create a cluster or a ring. So energy sources for microgrid, as you all know, majorly they are actually photovoltaic cells, winds, energy sources for microgrid. Okay, and you can connect them to the grid at any point of time. Now we'll move to the mathematical part of the modeling. Okay, PV cell modeling, which is very, very important. We have already modeled the battery. Now we are going to model the cell. So by not having the outside shunt series resistance, I can call it is a ideal PV cell. Okay, and if I connect it to the other resistance, it becomes a practical PV cell. So the difference between two ideal and practical is the current I, which is IPV minus ID, and in case of a practical, it is IPV minus ID minus I shunt. Okay, these are the two different equations, and rest of the things we can substitute and derive the equations. So sometimes, many students, especially they are in first year and second year, especially in first year, they're very intelligent students, and you are teaching constant voltage source and constant current source. And after the class, they come to the laboratory of the first year, and the lab actually they're asking the professor, please help me in understanding a constant current source. And please think of how do you satisfy your first year students who is very particular to see a constant current. Help your students to do that. And then we get into PV modeling where, as you all know, there are two types of characteristics for PV. One is actually VI characteristic and the other one is going to be IV characteristic, we say. The second one is going to be the PV curve. Okay, and from the PV curve, we can track the maximum power. And even from the IV curve, actually, you can track the maximum power that happens during V maximum point. Okay, so that's the corner point. We just note it down. Diode current, IO reserve saturation current of diode, Q electron charge, diode ideality factor, VT, RS, RP, V, and I. So these are different. Then similar to type of wind systems, you need to understand. So there are different type of wind system. Why I'm teaching all this? Because slowly when I move to a couple of classes from now, there will say, okay, this is a microgrid which has many other three cells, we have three lines. This is basically fundamental components related. So fundamental component. To understand the squirrel, which is fixed speed and variable speed, the first one, and the second one is going to, and finally it is going to be a synchronous machine type of fixed speed and variable speed. So representations of different types of wind machines. So there are 6 different type of wind machines. Again, Manmohan, if you test with one wind configuration, you can make it 6 wind configuration. We were successfully experimented all 6 in our laboratory today. And we have actually kind of, basically 2 machines. One is for induction type, one is for synchronous type, and then rest is actually network arrangement. You can experiment different combinations, not combination, different type of wind machines being connected to a grid. Modeling, as you know, I mean, it is going to be the mechanical power output equations. I'm not getting into detail. Or I can say, it is something like actually your mechanical power output, depends on the wind velocity. And similarly, the torque equation, and finally, the performance coefficients. Now, moving to fuel cell, the third type, which is very, very important. There is very little mathematics here. One is actually its substance, that is electrolyte substance. The electrolyte substance usually defines the type of fuel. Okay, based on that, we say X fuel cell is based on the substance. And the fuel that is being used, that is hydrogen, am I right, in most of the cases. So the most ions usually made up of, very fine platinum powder. Okay, the cathode catalyst, it turns the ions into water or carbon dioxide. It is often made up of the platinum. Okay, so we are focusing into only 3 different types of renewable sources, but probably one can think of beyond. So we are talking about actually fuel cells, we are talking about PV, we are talking about wind, different type of things. And then quickly, I will just rush you to some of the concept, electrical model of a fuel cell. So this is how actually the fuel cell being represented. The electrical model comprises of a number of elements which represents the thermodynamic and electrochemical phenomena occurring in the fuel cell, because the process is altogether different, as well as the consumption of the peripherals. This model reduces the FC fuel cell electrical performance based on the current demanded and the FC operating. But still, this is how it is being represented. We are not working on too much of mathematics because and if you like to do research on your BTech project or MTech project or PhD, then I will strongly recommend to work on this architecture. We will also try to understand in a microgrid 3 different type of loads: constant current load, constant power load, and constant impedance load. So when I talk about DC grid, not only generation that we talked about, but we also talk about the loads here. Okay, so I think you must be knowing what is constant current load, constant power load, constant impedance load. But for the benefit of some of you, those who do not have clarity, let me repeat it. In case of constant current load, because these are the 3 questions, whole life you are puzzled actually. All right. So where is its internal resistance to draw constant current? therefore the power varies. So I think in case of constant power loads, very constant impedance load is very interesting. Is a bulb or any um, a voltage which varies, keep on varying. As varies, the curve also can vary, and hence your resistance become constant or the impedance become constant. But the power varies because of V and I. Okay. So moving to a different type of converters very quickly, switched mode converters, just to, because this is not enough now. So when I talk about components, sources over, loads over, now the converters play an important role for DC to AC, AC to DC, DC to DC, AC to AC. Am I right? So different type of converters are required for any classical DC AC microgrids. Okay, so now we are focusing only on DC. So we'll see some of the DC DC. Losses incurred in linear mode converters. They are either series or shunt type. Switch mode converters topology is commonly referred as converter topologies. In general, DC-DC converters, non-isolated topologies are for higher switching frequency. So I think just all of you have an interesting look how classic DC-DC converter topologies, which works in such kind of arrangements. All of you please have a look. So we have a DC bus and connected with wind, fuel cell, battery, supercapacitors, DC loads, AC loads, and PV. So everything, you can use different kind of converters. So most of the cases you could see there is a DC-DC converter, there is a DC-AC converter, and that is what the whole arrangement is all about. So the first three DC-DC converters you could see, some of them are actually buck boost and buck boost type. Okay, these topologies are used marked in blue outline, utilize one of the classic converter topologies. So these are the converters are frequently being used for wind to DC, fuel cell, and PV applications. Those converters are being commonly used. So we can quickly see a bit of buck boost and buck boost converters. I mean, it is very my D. In case of boost, it is 1 upon 1 minus D. And in case of buck boost, it is D upon 1 minus D. It's a very standard formulas for all of you. And then we can slowly move into bidirectional DC-DC converters, because sometimes we have to give as well as take. So the key constraint for bidirectional DC-DC converters are it's a single converter, simplicity, take the creator. Converter. Some of the non-isolated bidirectional converter topologies are half-bridge. Now this is not enough because of microgrids, we talked about generations, loads, okay, and then we talked about converters, and then we talked about finally we need to have a little bit of communication network actually to make the microgrid operational. So all of you, dear students, try to understand. You understood different components, loads you understood, converters you understood, both one directional or single directional, bidirectional, both the types. And then you also understood different generations like PV, wind, solar, battery. So first one is consumer premises area network, which is applies to home area network, popularly known as AN, building area. And DLC, Bluetooth, Zigbee, Ethernet, and Wi-Fi are commonly being used under consumer premises area network. Then we can move to neighborhood area network, that is NAN, where communication technologies would support higher data rate. Okay, almost for 10 kilometers range. And this is Zigbee, PLC mesh networks are being used. Then we'll move to WAN, that is wide area network, which is very popular, suitable for future DC microgrid with large monitoring and measurement devices. Higher data solution and faster responses time is required. Speed required is almost 100 Mbps, and fiber optics, WiMAX, PLC, and cellular are. Now look into different bit of protections for LVDC. You also have fuses that cannot be ignored. We say everything is fine, but you do not have a fuse, then you circuit breakers, isolate low voltage one power module, case circuit breakers, and fuses. So these are also the part of your DC microgrid. And finally, applications. Okay, name few applications. One is your traction, electric trains operate with DC, data centers operate with DC, communication towers operate with DC, EV charging stations operate with DC, and finally the submarines also operate with DC. What are the challenges? Challenges are many. There is no standards, now perhaps actually it has been emerged, but still it has to evolve significantly. For AC, we have every standard. Every standard is known, but in case of DC microgrid, still we are working on because pilots are very limited. You don't have a city which is purely DC, and hence there is no standard can be easily be made up. Okay, so lacks of standards, protection issues, no DC circuit breaker in the sense, I mean, it is now available, but a couple of years back, actually, you don't have a perfect DC circuit breaker. You can go to the calculating current in parallel operation, grounding issues, unable to feed AC loads for industries, commercial and residential applications, high power loss in LVDC networks. So these are the challenges which pulls back the growth of the DC microgrid. But nevertheless, DC microgrid is certainly a solution for rural India. Okay, it is a solution for rural India where there is no grid available as of today. Thank you very much. Wonderful listening to, talk on. Now I can take a couple of questions from dear.
So thank you very much, sir, for a wonderful lecture on VMS and various components of DC microgrid. So is there any questions? Please ask. You can put in chat, unmute yourself and then ask. We are making slowly panelists to all of you. If any of you have any questions, please feel free to ask.
I think the details will be talking more, maybe probably in upcoming classes. But if you have any specific, I think someone asked me about the bidirectional converters. Who asked bidirectional converters? Can you please repeat, sir? Somewhere I saw a message. Because when you have a battery connected to a DC grid, it's a dual role, no? The battery will be charged based on the DC energy available in the grid, and parallelly, the battery can also discharge to the grid. Okay. So the DC grid and the battery need to be connected with a converter, which happens to be bidirectional. So that is what actually a separate scheme compared to a PV panel connected to a DC grid. You need a so no question. Hanji?
ACM series which
It will not work.
somebody.
No, it will not work at all. It will not work at all. The concept is no DC scheme, that is for sure. So that is what the challenges are.
Actually, it's expecting it still, it has been. So what about them? They need like waste.
Who?
So other than lithium-ion batteries?
Other batteries?
Yes.
No, lead acid we are still using, no. Our car is of lead acid.
Suppose like,
For example, tell me, nothing has to be thrown out in this country. They'll be used in a different application. Even the small battery with a very inefficient battery cell is still working. But cars are of lead acid, technology is still working. So we have decades of lead acid. Now we move to lithium ion. Even when we move to fuel cell, hydrogen gas, okay. So now it is easy, but if you tell me to ride a bike sitting on a hydrogen cylinder, it is very, very scary, you know. Good. Yes, please. Uh-huh.
That equation, what is battery charging at the same time?
Yeah, because you have physical battery. It cannot do both, no, simultaneously.
That is the screen is on and it is charging. It is giving the battery at a state, sorry, giving the energy.
No. This is my grid. These two are connected with a converter. Now this battery will take charge, either it is charging or it can discharge. Similarly, I have an electric vehicle. For charging, I cannot do both simultaneously.
But not
Yes, it cannot be.
charging on and the screen is on.
Let it be on. We are not worried about that. We are talking about battery. We are not. Battery, not an. I'm talking about a mobile, but I'm talking about the battery of that mobile.
Screen is on, it is taking part of battery.
Who?
Screen.
Screen is, the battery is getting charged. We are not talking about screen here. We are talking about the battery is getting charged from the grid or from the plug. That's all. Got it? You can ask again and again. So you have a socket and you are charging the battery. Now I like to give some power to the socket. That also I can do it. आप यहाँ पे आ गए एक्चुअली, वो भूल गए, सॉकेट भूल गए एक्चुअली। लेने के टाइम एक्चुअली इस तरफ आ गए, लेने टाइम तो सॉकेट से बैटरी को लिए, देने के टाइम बैटरी टू सॉकेट होना चाहिए, नॉट स्क्रीन। हाँ, do optimization problem solving, that laptop is not understanding the reality. It will say, like you, it will say it can charge and discharge because it wants optimal solution, no? But we know that it cannot do both. So उसको restriction लगाना है algorithm. वो restriction लगा रहे, you are forcing the battery, okay, either charge or discharge, not charge and discharge simultaneously. Good. Anything else? So with this note, we come to an end. Thank you very much for your patience.
Listening
of today's lecture. Looking forward to see you again. Thank you, Abhishek. Bye-bye.
Thank you, sir, once again. So, dear participants, with this we end today's talk, and we'll meet tomorrow again at same time 5 o'clock for day 5. Thank you.